Okay, so in this chapter we've seen how to do some antiderivatives. We've also seen how to most recently evaluate some definite integrals through the major idea from the fundamental theorem of calculus. And in this section we're going to be doing both. We're going to be doing some antiderivatives and some definite integrals, so indefinite and definite integrals. But this time it's going to be, the integral is going to be a little bit more complicated. So we're going to need to use a technique called integration by substitution. Now, this is actually the exact same thing as me saying we are going to learn the reverse chain rule. So remember in chain rule, if you ever have a composite function, something like, I could write it like this now, capital F of g of x. If we were going to do chain rule on something like this, the derivative would be the derivative of the outer layer evaluated at the inner layer, so that would be f of g of x, and then multiplied by the derivative of the inner layer, so multiplied by g prime of x. So you can see that given what we know about chain rule, it makes sense then that the integral of something in this type of a form is going to be equal to capital F of g of x plus c. So the main thing that we're going to be doing in these problems is we're going to be trying to recognize when we have composite functions in the integrand. And if you can recognize that you have a composite function in the integrand, kind of like what you see here with this f of g of x, then there's going to be a process that we can follow. And this process is going to be called a u substitution process. And we will let u equal the inner part of the composite function, and then we will let du, if u is equal to g of x, then du is equal to g prime of x dx. I'll show you what I mean. So if I'm starting off and saying u is equal to g of x, I can take the derivative of this with respect to x, and I could say that du dx would equal g prime of x. And that is identical to saying du is equal to g prime of x dx. And so if we have something like this to start, where it's the integral of f of g of x times g prime of x dx, and we know that we're going to substitute in u for g of x, this is going to become f of u, and then g prime of x dx can get substituted out for du. And that's because if u is equal to g of x, then the derivative of u with respect to x would be g prime of x, or in other words, du is equal to g prime of x dx. So basically, this whole thing is going to convert into the integral of f of u du, and then you can actually integrate this. And so the process that we're going to go through is going to be this u substitution process. When you integrate, you'll end up with capital F of u plus c, and that's when you're going to back substitute in what your u is actually equal to. So you'll end up with this capital F of g of x, and again there's a plus c after that. So this is the very abstract way of kind of describing what we're about to do in a lot of these examples, but you only want to go through this abstract process, this u substitution process, when we see composite functions in the integrand. So let's take a look at some of these examples. In example 1, we actually don't have a composite function in the integrand. I mean, in this problem, I would most likely just distribute the 2x through and do the integral this way. I would say, let's see, what would that be? 2x cubed minus 18x dx. So I probably would not do a u substitution. You actually could here, and part of the reason I put this example in here is you could do it both ways. You could do it this way, or we could do a u substitution, but the fact of the matter is, if you can do it the older way, where you're simply using power rules and things like that, then don't overcomplicate it. So in this problem, I'm going to just do the antiderivative here, so that's going to be 2 times x to the 4th over 4 minus 18 times x squared over 2. We'll put in a plus c. So this answer is going to be x to the 4th over 2 minus 9x squared plus c. So that's just what you've learned already going back to the very first section of chapter 5. But contrast this example with what you see here. In this problem, there's no way you're going to take x cubed plus 5 and raise it to the 4th power and expand all of that out and then distribute an x squared and then do the antiderivative of each piece. So here, you look at this and you say, you know what, this is a composite function right here. Maybe I can do this U substitution strategy. Maybe what we see here is a result of doing the derivative of a composite function through the chain rule process. So let's do reverse chain rule. So I let u equal the inner part of the composite function. And so in this case, u is going to equal x cubed plus 5 because my composite function is x cubed plus 5 to the 4th. Now, if u is equal to x cubed plus 5, what is the, don't look back at this, just look at this equation right now. What is the derivative of u with respect to x? Well, the derivative of u with respect to x, du over dx, would be 3x squared, which means if du over dx is equal to 3x squared, then we can also say that du is equal to 3x squared times dx. Now, when you look at the integrand, we're going to make a substitution for u is equal to x cubed plus 5, but then I would also like to make a substitution for something that has, I'd like to see 3x squared dx in that integrand, because if it was there, then I could simply plop du in its place. And so I'm going to try to make a couple of substitutions here, and here's how I'm going to do it. Well, the x cubed plus 5, that's just going to go in here, and I'm going to write this in there as u to the 4th in just a second. But notice the rest of the integrand is actually just x squared times dx. I wanted 3x squared times dx. Here's the cool thing. We can make this 3x squared. Look at that. I've got a 3x squared times dx. But obviously you can't just multiply something by 3 without offsetting that somehow. So if I multiply it by 3 in the inside, I can offset multiplying by 3 by putting a 1/3 in front of that integral. And now watch, this problem becomes 1/3 times the antiderivative of, now I'm actually skipping over to the x cubed plus 5. The x cubed plus 5 is my u, right? Because u is equal to x cubed plus 5. So u to the 4th, and 3x squared dx can be taken out, and in place of 3x squared dx, I'm going to put du. Now this is a pretty easy antiderivative, right? You would say 1/3 times u to the 5th over 5, and so that's u to the 5th over 15. We would say plus c, and you would be done, except for the fact that I don't want an answer in terms of u because it wasn't the original problem expressed in terms of x. So let's back substitute what u is equal to, and u is equal to x cubed plus 5. So you end up with x cubed plus 5 to the 5th all over 15 plus c. This is our final answer. The best part about doing antiderivatives is we can easily check our work. If we do a derivative of this, we should get back to the original integrand. And if you brought the 5 down in front, you would end up with 5 over 15, so that would be a 1/3 x cubed plus 5 to the 4th, and then multiplied by the derivative of the inside, multiplied by 3x squared. And so you'd end up with a 3 in the numerator and denominator, those would cancel, and you would end up with x squared times x cubed plus 5 to the 4th, which is exactly the original integrand. So one of the big things you should be doing here is checking your work. And the way that you check your work in the end of these antiderivative problems is you just do the derivative. All right, let's take a look at number 3. Do you see a composite function in this problem? Do you see that 1 plus x to the 4th is inside the squaring function? So I would most likely in this case try letting u equal 1 plus x to the 4th. I can also see right away looking at that problem that this is not your typical antiderivative, right? Like I can't simply use the power rule or something like that. And so that's why I'm kind of jumping right away to looking for that composite function. Now if u is equal to 1 plus x to the fourth, what would du be equal to? Well, du would be equal to 4x to the third times dx. Remember, technically du over dx is equal to 4x to the third, but then I move that dx over. Do we have 4x to the third dx in the integrand? No, but we're close. We've got an x to the third dx. So I'm just missing that 4. But I can't put a 4 in there without putting a 1/4 in front. So this problem becomes 1/4 times the antiderivative of, let's see, 4x cubed dx. That is all my du. And then 1 plus x to the fourth is u. So we have du over u squared. Or what this is 1/4 times the antiderivative of u to the negative 2 du. Now we can use the power rule. This is an easy antiderivative. So I say 1/4 times the antiderivative of u to the negative 2. I'm going to add 1 to that exponent and then divide by that new negative 1, which is the same as multiplying by it. Okay, and then we would just say plus c at the end of this. And so this is going to be negative 1 over 4u plus c. But remember, we have to back substitute and put in what u is in terms of x. So my final answer is negative 1 over 4. Here, let me scroll a little bit. There we go. So we have negative 1 over 4 times 1 plus x to the fourth, and then plus c. So this would be the final answer to this question. And once again, if you wanted to, you could rewrite this as negative 1/4 times 1 plus x to the fourth to the negative 1. Take the derivative of that, and when you take the derivative of this answer here that we have, you should end up with the original integrand. Okay, one more right here. Number 4. The antiderivative of t cubed over 3 plus 1 over 4t squared. So do you see a composite function? You really don't here. I mean, in the last example, we had parentheses 1 plus x to the fourth raised to the second, or in the number 2, we had the parentheses x cubed plus 5 raised to the fourth. So especially when you have those parentheses, it's kind of your clue that you've got these composite functions. I really don't see any composite functions here. In fact, I think that I can do the antiderivative of this piece just using my power rule, and the same thing with this piece. So let's just try to do it the old way. So the antiderivative of this piece is going to be, I'm going to take that, the t cubed over 3, I'm going to write it as 1/3 t cubed. So the antiderivative of that is going to be 1/3 times the antiderivative of t cubed, which is t to the fourth over 4. And then here, this is 1/4, I can think of that as 1/4 t to the negative 2. And so the antiderivative of t to the negative 2 is going to be t to the negative 1, because you add 1 to that exponent, and then you divide by negative 1, which is the same thing as multiplying by negative 1. So it looks like my final answer, there's no substituting or back substituting here, it's just t to the fourth over 12. And then it looks like we'd have minus 1 over 4t to the first plus c. Once again, if you're unsure, like maybe I am right now, I'm going to just take my derivative and see if I get back to where I started. So you'd have 4t cubed over 12. That's the same thing as t cubed over 3. And then this is the same thing as minus 1/4 t to the negative 1. So that derivative would be positive 1/4 t to the negative 2, or t cubed over 3 plus 1 over 4t squared. And yes, that's exactly what the original integrand is. So I know that I definitely got this question right. Okay, in the next video, I'll take a look at some more examples on the back of the notes.